Hey guys, in this part of the video, we are going to be looking at the conductive heat transfer over a flat plate with this laminar flow due to the local Nusselt number, um, a Nusselt number, my bad. Um, and essentially, we're going to try to maximize the heat transfer over this plate and prove that the flow should be oriented perpendicular to the longer edge. So. Before we start doing the math to prove that it being perpendicular would be optimal for heat transfer, what I'm going to do is do kind of a more advanced Buckingham than we did last time in the previous part for this assignment. As you can see, we have heat transfer, we have thermal conductivity, and heat capacity, which means that on top of mass, length, and time, we now have to consider a fourth dimensional group, temperature in this case, when we're making our dimensionless groups. So we have the null set number, we have the particle number, and we have the Reynolds number. And we're going to try to make dimensionless. I wanted to just do this part to kind of prove that these are dimensionless and how we would acquire the units for this so that you can then do a dimensionless matrix to then obtain these values. So I'm going to look at the conductive heat transfer. This is heat flux equals what is a conductive heat transfer times temperature. So this is joules per meter squared per second. And then to get just H, we would also divide by temperature on both sides to get H. And so now we have this number, and what we can do is turn joules into newtons per meter. Put that in meters squared per second per Kelvin. And we can cancel the square, remove the n. Newtons equals kilograms per meter per second squared. And when we apply this, we get rid of the m here, we get rid of the n here, m here. The kilogram seconds cubed per Kelvin. So if we go to our Buckingham analysis, we have one, there's no meters anymore. Seconds, we have -3. And then for temperature, we have -1. So let's go ahead and do the same thing with the conductive heat transfer. No, sorry, the thermal conductivity. Sorry. Thermal conductivity. This is going to be joules. Uh, oh, I actually wrote it down already. Joules over meters Kelvin a second. And so we're going to do the same thing. We're going to convert this to newtons meters. That cancels out those meters, and we're left with Kelvin per second. We turn this into kilograms per meter over Kelvin over seconds cubed. When we turn this into kilograms per meter, which we already canceled out, kelvins per second squared. Oh, wait, no, this is just second squared. And we're left with this for the Buckingham to insert. So we have 1 kilogram, we have 1 meter, we have -3 in the seconds because it's to the power 3 in the denominator, and then we have -1 for Kelvin. And then for heat capacity, this is heat equals mass, or this is energy equals massive times heat capacity times change of temperature. And so to just get heat capacity, we would just divide joules by mass, change of temperature, and this would be seconds. So this equals heat capacity. When we do our analysis, this would be Newton meters over kilogram times change of temperature times S. This then turns into kilograms meters squared over seconds cubed times kilogram times Kelvin. We remove the kilograms now, or just left with meters squared over seconds cubed multiplied by temperature. So this is 0 to, just making sure I'm not missing any units over here. Should be good. -3, -1. Okay. Actually, no, this is just heat, so it's there's no S over here. So this would be Sorry, this would be squared. We're trying to be as correct as we can be for the Buckingham. And then we know these other groups, we did this in the previous part. Pressure is kilograms per meters cubed. Length is simply just meters. Viscosity is kilogram per meter per second. And velocity is meters a second. All right, so you would use this to make a dimensional matrix to then get your dimensionless numbers, which are the null set, Reynolds, and Practal number. So now that we have these values, we have this equation for laminar flow over here, which I'm going to go ahead and drag really quick, just so we can use it. We have this flat surface, and we're trying to find the best conductive heat flow with laminar flow in this case. And we're trying to say that if it's oriented perpendicular, it will achieve this better. So let's think of it like this. If we have some liquid coming through, say I have like a bunch of something about to have contact with the plate. What I know from the principles of mass transfer is that the immediate contact here, velocity will equal zero. And as this begins to spread across our system, we have a boundary layer which has a velocity gradient like this. And the difference in velocity will become greater and greater with regards to the plate, and this gap will increase square root of the distance that we have. So basically, as we continue to move this liquid across, the boundary layer's velocity gradient is going to get greater and greater and greater, square root to distance that it is created. So obviously, that's not very good. If you were to think about it like this is essentially saying that as we get longer and longer this way, this the thermal, what is it, the heat transfer conductivity is getting weaker and weaker and weaker. Well, why is that? If we go back to the dimensionless numbers that we solved for, let's go ahead and put this in just raw units. We have 0.332. And I'm going to leave these in the unitless numbers really quick. So when I have h of L in this case, I'm going to say that for this plate over here, I'm going to say that this equals X. I'm going to remove length really quick. I'm going to say that this is H multiplied by X. What I can do is I can go ahead and simplify this expression. What I can do is move X over to the other side. Specifically, what I can do is, oh wait, actually, sorry, let me make sure my math is right here really quick. Sorry, I forgot, I wanted to make an assumption really quick that there are no edge effects. Forgot to say that for this dimensionless plate. Um, what I'm going to do is I'm going to move X over to the other side because if we do that, we can see what properties happen over when we shift it to the other side. And so before I do that, I'm going to go ahead and expand all terms really quick. I'm going to say Reynolds number 0.332, and this is going to be, all this will be the group of 1/2. So this is pressure, velocity, and change of pressure. Viscosity, power 1/2. And this is the thermal conductivity group. And so if I were to go ahead and take X and move it over to the other side, what I can say is, sorry, remove X over here and move to the other side. This is the power of negative 1/2. Well, 0.332 volume density. Actually, no, it's fine. I'll just erase that over there. So if we analyze what's happening to our value, as X increases, our thermal conductivity gets lower. Because look at what it does to the algebra here. If this increases, this entire function and therefore heat capacity gets smaller. So what that tells us is that H is greatest at the beginning. So if we're thinking about this plate here, thermal conductivity is best when it is around this group. So we can say, okay, we need this pipe to be as wide as possible as it is flowing through, and we need to only continue it for a little bit and have it be perpendicular flow until it absolutely needs to turn the other way. So if you were to have a system, rather than having long, narrow pipes, which would not ruin, but you would have less efficient, uh, you would have less efficient conductive heat transfer throughout your system versus if you had wider and shorter, your boundary layer isn't creating this change of distance and velocity gradient over time. So that's why for this system, it would be optimal if flow was to be perpendicular to our system.